I'd like to invite our second panelist to join me on stage now. As they're getting configured, I'll quickly introduce them. And as Chris mentioned, they are the mad geniuses of vertical lift. Mark Moore, NASA Langley Research Center, Matt Baldwin, Joint Aviation Systems Integrator, National Geospatial Intelligence Agency, Professor Anubhav Datta, Associate Professor, Alfred Gesso Rotorcraft Center, University of Maryland. And our very own mad genius, Patrick Tucker, he's our technology editor at Defense One, will be our moderator this afternoon. Thank you, gentlemen.
Okay. Thank you so much. Thanks for sticking around. It's good to see so many people up and awake and looking forward to talking about the future at this hour of the morning on a Tuesday is always very encouraging. So I want to express my sincere appreciation for the panel being here. We're going to have everybody go down the line and very briefly talk a little bit about themselves. There's some slides that we'll get into as well. Let me explain my angle on all of this. I am technology editor at Defense One. So I cover how emerging technology changes the national security environment today, 10 years into the future, 20 years in the future. Now, before that, I was a editor at a magazine called The Futurist. And when you edit a magazine called The Futurist, you get one question a lot. What do you think it is?
Where's my flying car?
Where's my flying car? Thank you. That's it. Where's my flying car? So if you think about what a flying car is, if you don't have a runway, then you're talking about a vertical lift platform. That's the whole thing. So I was asked this question over and over again. Where's my flying car? What happened to it? When did I get it? And finally, I met a guy that had made one. His name was Paul Moeller. He lives out in California. He's still making these things. It's pretty incredible. And the flying car that he made was called the Sky Car. And basically, it's sort of like an Osprey, like everybody knows a V-22 Osprey. It's got two great big propellers, and they tilt up like this to achieve vertical lift, and then they go forward like this to achieve forward momentum. Except on the Moeller Sky Car, the propellers were about this big, and there were four of them on the side of like the cab of the car. And they would spin really fast to achieve vertical lift, and then they would tilt forward like an Osprey, and they would propel you forward that way, and it could achieve about 300 miles an hour. So I asked him, well, congratulations, why can't I buy this thing today? And he said, okay, here's the thing. Once you reduce the diameter of the propeller, you have to put more energy into the machine to achieve thrust. So every time he reduced the propeller size by half, he had to increase the amount of energy he was putting in by about 60%. And so the only place where it was economically feasible to have his invention was Dubai, where they had an abundance of energy that they could readily draw from to power these things, and also where there was no FAA and very few tall buildings. So with that in mind, I'm so pleased today to see this panel. We're going to get into this question of the physical limitations of future vertical lift craft, how we overcome those physical limitations through the use of information technology, the use of better computer modeling, new techniques, and we're really going to expand our understanding of what a helicopter is to platforms that today would seem speculative but are actually very realistic. So with that in mind, let me welcome first Mark from NASA, Mark Moore, and tell us a little bit about what you do at NASA and about the awesome experimental aircraft that you're making over there.
Okay, I've got a couple of slides I'm going to bring up.
There we go.
So just a little bit about myself. So I've been working powered lift my entire 33-year career at NASA. That's all I've done. That's all I love. And the last 5 years you can see on the screen behind me. And so I am very much a cowboy from the Wild West, here to tell you stories of what's going on in this crazy frontier of distributed electric propulsion. Frankly, the last 30 years in terms of powered lift aircraft have been all about the tilt rotor. I grew up working on the XV-15 at NASA. We have the V-22. And besides that, powered lift fixed-wing aircraft have been in the doldrum. And if you look at what happened in the 50s, 60s, and 70s, wow, what an exciting time. But you can't have new capabilities and have great new breakthroughs unless you have new technologies. And that is what my entire message is that distributed electric propulsion is a wild and wonderful, fundamentally different propulsion technology that changes the rule. I mean, you talk about high and hot performance. How about if you don't have an air-breathing engine? You know, and high and hot doesn't even matter at that point. Really, really huge changes in what this propulsion system can do. And most importantly, for what the vehicles that you see that I've been leading in the past 5 years, it is a scale-free technology. You know, it doesn't care what size the motors are. They're going to be 95% efficient. They're going to be 4 horsepower per pound, great specific power, really compact, really reliable, single moving part. And that's why we can do these crazy vehicles that we're doing, because you don't have to centralize propulsion anymore. You can distribute it to put it wherever you want to achieve great control forces and moments and efficiencies gains. So, okay, so I didn't do the CL84, but it really shows, you know, as you implement this new technology to be able to distribute however you want, you can take old ideas and make the problems go away. Why don't we have CL84s flying around? Because it was a mechanical nightmare, and it experienced a transition buffet like crazy. Well, now we can completely eliminate the transition buffet by distributing the propulsors across the entire wing. I'm going on too long, but really exciting vehicles, so I'm just going to tell you a couple about them, especially about this Mad Max experience down on the bottom. If you see that truck and you say, wow, what a crazy idea.
Yeah, look at that.
NASA has, and the DoD, for what, 50 years, we've been doing extravagant high lift systems to achieve extreme short takeoff and landing, right? And great things, circulation control, externally blown flaps, 5-element flap systems, really cool, and they work. But guess what? You have mechanical nightmare in terms of complexity. And another thing, you have pitching moments that make your tail almost as big as your wing. Well, as we implement distributed electric propulsion on this mobile test rig that we did, we were able to go from, you know, a nice flap system achieving 2.5 to 3, to, once we implemented the power effects, up to greater than 6 coefficient of lift. So more than double the amount of power, and that's not putting that much power into that distributed electric propulsion system. But what's really cool about it is there's no mechanical complexity, no cross shafts, no gearboxes, and there's no increase in pitching moment, because we're cheating. We're effectively increasing the dynamic pressure that the entire wing is seeing, instead of trying to turn it at the trailing edge of the flap and creating this huge nose-down pitching moment. So really new, exciting capabilities when you talk about extreme stow. And, you know, this is the next place where we're taking distributed electric propulsion with the X-57 NASA demonstrator. And what's really cool about this capability is you can see what we're able to achieve in terms of the change in efficiency, the change in where that efficiency occurs in terms of the speed, and effectively achieve a 50% improvement in lift-to-drag ratio over the base aircraft that we're starting with. So I'm already going long, so I'll just say, you know, we're learning by doing. You know, a lot of people say, oh, electric propulsion, you're going to have wires this big that are taking up the whole. Actually, it's very compact. You go to these high voltage systems, really exciting lessons in EMI and other integration problems.
This is good. Keep on this one. This is great.
How does this relate to vertical lift? Well, one of the things that you may be skeptical, but you've got to pay attention, because Silicon Valley has woken up and decided that they want to do aerospace. And so you have all these Silicon Valley companies now jumping in to do these fixed-wing VTOL distributed electric solutions.
Yeah.
And what's really cool is they don't know all of the horrible things that relate to powered lift. And so they're absolutely convinced they can do it. And actually, it's the perfect time to question whether they can. Autonomy is a really cool new technology. You're seeing big players like Airbus and Uber step in, but the reason why this is so exciting and why Silicon Valley is doing this is because we do have the opportunity to invalidate the helicopter. It is, as much as I love them, they are a pathetic flying machine. They have horrible lift-to-drag ratios. They have horrible noise, vibration, and harshness issues. They're horribly inefficient in every way, and we have the chance to do much better with this great new technology.
Okay, awesome. Thank you so much, Mark. So the interest of Silicon Valley in achieving new types of vertical lift, it really can't be overstated. What was it? Yeah, 2 years ago, I was in Atlanta for a big drone conference. It's kind of the seminal unmanned drone show. And you've got interesting folks from all around the world with these really fascinating platforms. And who's walking the aisle but a guy that I know named Sebastian Thrun, who's the guy that invented the first self-driving car for DARPA. And with him, his boss at Google, Sergey Brin. So this is like a key interest of like the
Larry was there too.
Yeah, that's right. Larry was there too. This is a top interest of key intellectual forces in Silicon Valley because information technology, when you think about what you can achieve with where that's going the next 10 years, you start to push against physical boundaries that have imposed limitations on us for a very long time. And on that note, I'd like to ask Dr. Nubab Data to talk a little bit about his work at the University of Maryland. Go ahead.
So 4 years ago, I was still at NASA Ames and working for the Army. So the Army, NASA, and Air Force got together, took the Black Hawk rotor, slowed it down to 40% of its RPM, and flew it at an advance ratio 3 times that it's supposed to fly, with the entire retreating side under flow reversal. The rotor held. It's a good rotor. And gave us a glimpse of how helicopters might fly in 2030 and beyond. I want to remind you, we are the only aircraft that are designed to fly in transonic regime. Everyone else either flies lower or higher. We fly right into transonic flow. But I'm in Maryland now, so we have the Al Gesso Rotorcraft Center. He was a pioneer, and let me give you a That's not my chart.
You're going backwards.
Oh, yeah.
Okay.
Right. Yeah, we're going backwards.
You're going backwards still. Nope.
Yeah.
Go the other way.
Yeah.
Keep going.
Keep going. The future helicopters back up too. Yeah.
Okay.
There we go.
So our core mission is to train the next generation of engineers. And we are also a research university, so we have a broad portfolio of interdisciplinary and multidisciplinary research. Our main technology transfer is students, and one example was our speaker, the last speaker. But we also want to insert solutions of key barrier problems as fast as possible into the US industry and government. Overall, we have about 9 faculty. I would say about 4 or 5 dedicated to rotorcraft. So it's a very special department. Our annual expenditure, research expenditure, is around 8 to 10 million. We are a university, so. If you think of what is our key strength, it's experimental facilities. So we have a balance between analysis and experiment. And the Glen L. Martin Tunnel, which is a 7 by 11 foot subsonic wind tunnel, many of the Sikorsky tests are also done there, up to 200 knots. So many of our experimental facilities are built around that. So finally, we take our rotors and do max scale tests in that tunnel. And of course, many other facilities are in the works. We are since 1982, we are an Army designated rotorcraft center of excellence. Currently, it's Army, a little bit of Navy, and a little bit of NASA. But pushing and breaking key barriers for Army aviation is one of our core missions. And just last week, we had a kickoff for the next 5 years of research. So let me give you a very top-level overview. There are 5 core areas that we're going to invest in as we train students and break barriers in the next 5 years and beyond. One is, of course, coax. I think earlier you saw a picture of a coax being tested in the Glen Mountain Tunnel. So these are not the old, this is the new X2 technology. These are hingeless blades, what are called lift offset rotors. And one of the problems with them, as good as they are, is that they fly at the expense of very high hub moments. So if you try to scale them up, you have difficulties. So we want to break those difficulties and control the loads. We are also setting up a tilt rotor test rig. So these are tilt rotors of the future. 2 of the main hurdles in tilt rotors now is, number one, we fly with a very thick wing to avoid wall flutter, 23%. Well, that's not good enough to take me to 400 knots, where we dream of flying. We need about 15% thin wings. So we are looking into new kinds of rotors that will get us there. These rotors are great, but they're very expensive. These are gimbaled, flexure cones, stiffened plane rotors. So that's the second core area that we're going to invest in. We heard that Apaches and Blackhawks are going to be there for a long while. We'll still call them Blackhawks and Apaches, but the technology is going to be very different from today. So we have a lot of investment on what we call slowed rotor technology. If you go through the key barriers, one thing that hits you eventually is cost. And everything is becoming more expensive except processing power, raw processing power. So one of our major thrust areas is to develop very high fidelity simulation tools that we envision in 10, 20 years will be used not only design and flight test and load survey this aircraft, but even taken up to certification. So that's one of our major areas. And that's in sync with the National Strategic Computing Initiative, and there are many other key players, IBM and Intel, poised to give us the power we need to tackle very complex helicopter problems.
Okay.
So that's methodology development. Lastly, of course, electric. This can be a very disruptive technology, and no one can tell you better on this topic than Mark himself. So right now they're very heavy, but technology is moving very fast. And so we are keeping an eye on it, and from this year onwards, we will have a dedicated program to try and improve and break some of the barriers there. So I'll stop with that.
Thank you very much, Dr. Datta. And now let me turn to Matt Baldwin with the Joint Aviation System Integration Office at NGA. And so one of the big trends that we talk about in terms of the future of vertical lift for the military is unmanned capabilities and also the use of these systems for ISR. And that puts just a bunch on your shoulders to get data, to figure out what data is useful for creating more autonomous solutions, to structure it, and then also to work these things. So what do you see as the key challenges to different types of platforms for the next 10 years, and how do those challenges confront you today?
Okay. Ladies and gentlemen, good morning. Lieutenant Colonel Matt Baldwin. You said I worked in a Joint Aviation Systems Integration Office. It's actually a cubicle, and I sit in it. I'm also the guy that gets to sit between two smart people. So the issues that we see today, that I'm personally seeing is, one is we don't know what we don't know as far as what's capable, the art of possible, and getting there. And then once we start to figure that out, how do we better communicate that back to the services for the requirements generation and moving through the acquisition process. For instance, I do quite a bit of work with the FEL project, sit in, basically a fly on the wall, waiting to hear for any geospatial type requirements. Most helicopters that we fly in the Army today use DTED, which is the digital terrain elevation data, to be able to tell systems how high you are off the ground. Where I sit now, DTED is a legacy system. It is dead. if you will. We have remapped the world a couple other times, and we have elevation data that's more precise. So, of course, the question is now, why can't we take that and just give it to the services and let them use it? NGA is very agile. We can create new stuff. Unfortunately, the acquisition systems and the services aren't fast enough to keep up. You talk about elevation data and having to totally gut Apache computers to take this data in. It's just too expensive. So we'll still continue to provide DTED until such times that we can now integrate new stuff. So that's where I sit at my cubicle, to try to convey to the services that this is what we know. This is what we've all grown up with, and it's kind of like that warm bear that you just want to go up and hug. But we've kind of got this new stuff that's coming out that's more precise, and with the invention of small satellites, being able to traverse the Earth numerous times in a very, very short period of time is going to lend itself to even better data, not only elevation data, but other types of geospatial type data sets that the services are looking for.
So you have elevation data on like the entire world?
Yes, sir.
It's just sitting there in like your cubicle, and we don't have like an ability to get this.
My cubicle's not that big, but.
Yeah. And we don't have right now an ability to get this on board like the computer system of an Apache?
We do, yeah. I mean, but
it's not easy.
It's not that it's not easy. We can put DTED on the systems now.
Yeah.
However, DTED is old.
Yeah.
The data is old.
Okay.
I'm trying to draw a parallel for you that you guys could understand.
You're looking at an old map. Is that fair?
The iPhone 2 still works.
Yeah. Right.
Right? But why?
Yeah.
So it still works. It still meets the need.
But wouldn't you rather have this?
But wouldn't you rather have that?
Yeah.
So if I can provide you a better data set that's more precise.
Yeah.
If we're talking about autonomous, systems, we need very precise elevation data.
Yeah.
There's a difference between a foot.
Yeah.
Right.
Okay. That's interesting. That's so fascinating that we're sitting on an entire global map of elevation data, and we have trouble utilizing it to its fullest potential right now. That's, I think, a big problem area to solve for the industrious folks in the audience. So to you guys, I'm going to ask some questions, but rather than wait till the end to open it up for questions, if you have a question, raise your hand. We're going to try and get to you, because I think this sort of panel is definitely more fun when everybody starts participating with these ideas as they spontaneously emerge. So yeah, shoot, we've got one in front already. Oh, hold on there. We're going to get you a mic so that we can record your question real quick. All right. That's all right. No. Right here in front.
So this question is really for Mark, but going back to Patrick's original question of where's my flying car? I guess a two-part question. When do you see this being applicable or available for service? And then how can we get people to stop calling them flying cars?
That's what I want first. Let's stop calling it flying cars because they mean many things to many people.
Right.
What's really exciting is, over the last 5 years, it's great because my job at NASA has been to work with all these different companies developing all these new concepts and get to know them, help them out. But something really big has happened this last year, and that is not just a couple new companies have come to create new vehicles, but the end user market has come forward via Uber to say, this is exactly what we need, and if you can build us this vehicle, then we can work with our customer base and prove that it's an economically viable business case and show that there's strategies to work with the FAA and the cities to make this whole ecosystem a vibrant market. And that is a game changer. So if you haven't read the Uber Elevate white paper, it's on the internet. It's 100 pages of really dense talk about, smart but plentiful talk about the barriers and how to overcome those barriers, and their complete decade-long plan to create the marketplace in collaboration with cities, with these new vehicle developers, with the regulators. And it is the emergence of this collaborative ecosystem that is exactly what's needed. And so I believe Uber will be completely successful over the next decade and bring about a whole new type of vertical lift market that is vibrant. And because as you pointed out, right, just this past year, 40% decline in civil rotorcraft sales just because of oil services. We need a more vibrant customer base across vertical lift, and I think Uber's the one who's going to pull it off.
So is it too much to say that as Silicon Valley becomes interested in this as an international market that they could fulfill, that that's going to push innovation that then the military as a customer will be able to take advantage of, but as long as the military is the sole customer, it stifles its own innovation?
Well, that's a great point, because in the past, from my perspective, being in the vertical lift community my whole life, the 800-pound gorilla has been the DoD in terms of technology development. I think that's being flipped on its head. And I can tell you, there is power in consumer markets. You think the DoD has a lot of money? Look who really has the money. And so when you can create vibrant consumer markets, the DoD has a chance to leverage that. That's why you see them initiating things like the DIUX,
Right.
which has offices in the hotbeds, Cambridge, Silicon Valley. There's really fantastic early applications. Like, we're already working with the special ops guys because I know that I can create a vertical lift distributed insertion vehicle that is insanely quiet, 20 dB quieter than the best helicopters. That is really a cool capability. If you want to be able to hover at 15,000 feet without any problem, that is a really cool capability for special ops and others. So there's some early adopter missions and markets that could be really, really powerful to leverage what's happening in the Silicon Valley.
When did you start working with the special operations community on an experimental vertical lift plan?
We haven't, I didn't say we've been talking to them.
Okay.
So we haven't been starting an experimental effort. It's like any of these projects. The first thing that we do is we start by understanding the user needs, because we've got this brand new widget that can go in 1,000 different directions.
Okay.
But we want to tune it to what their needs are.
To the extent that you can, what do they tell you that their needs are? Persistent stare, I imagine.
So being able to have ISR, but very quiet and very close is an interesting mission. But I can't go into all those discussions.
Okay.
But actually, what's really, really cool, I'll say, is that we're not dependent on them or DoD to come up with the funding to make these experimental platforms a reality.
No, but we've still given a nice journalist a good headline today. So if you're out there, you can get to work.
Again, it's a really exciting time where we can embrace public-private partnerships to really push the technologies very rapidly.
Yeah.
These companies are very aggressive, and frankly, having worked for the government my entire life, I can say we're a bit conservative in terms of new technology frontiers.
Okay. At the same time, though, this is great cause for optimism, but there are some hard threshold challenges that seem really difficult to overcome. And a good example, we saw a couple of slides of it up here. There's a DARPA, a Defense Advanced Research Projects Agency, vertical lift challenge. And the goal of that challenge is a vertical lift aircraft that can lift 4,000 pounds, 40% of its own weight, and move at speeds of 300 knots. And we were talking earlier about speeds of 400 knots. Why is this a difficult challenge? And how do we overcome it?
Well, why is the speed a difficult challenge?
Yeah.
Because for helicopters, because of retreating blade stall, and rotors simply are not effective at going fast. And I mean, yes, you can set the world speed records, at 240 or Actually, going back to the Army, they've set prior helicopter speed records, but you're up against a brick wall in terms of drag.
Right.
They have lift-to-drag ratios of 4 at their optimal cruise speeds. It just is downhill from there.
Right.
So, I mean, you can always throw more power at it, but the solution of vertical lift is to come up with more elegant solutions that you don't just throw power at it, but you're actually, as Mike pointed out, you're developing lift from wings, which are always going to be way more effective and efficient than rotors at high speed.
Dr. Zadok, what is your opinion on this? Why is this, how do we achieve higher speeds than we today are used to with vertical lift planes?
So let me give you a few numbers. First of all, if you combine the best of electric technology from everywhere, from Navy, HTS motors, automobiles, and for a 2 to 4 seater airplane, you get about half power to weight ratio from a piston engine. That's not bad,
Right.
but it's half. The bigger problem is if you carry half the payload, you can only go half the range. So
Right.
it's about 1/4 productivity. But technology is increasing every day, and things may turn around. And for certain boutique strategic missions where silence, maybe safety, agility is very important, that comes into play. Now, in terms of helicopters, I think it is a little bit of a misconception that forward speed is limited by dynamic stall. It comes down from very old tests at the Langley. I think the forward speed is mainly limited by advancing blade transonics. And Sikorsky has shown that you can take stall out of the equation using 2 rotors. And the technology of slowed rotor is going to get you below the advancing blade drag divergence. So I won't discount. I think helicopters can, they're already flying at 250 knots on an experimental basis. And I'm quite sure they can be pushed to 300 knots. Tilt rotors, we're going to see flying at 450 knots. So I think those are 2 separate issues. Electric engines in flight can enable both fixed wing and VTOL aircraft in future for certain curtailed missions.
Okay. So on this power question, because we're talking about all of the processing power that we want to have on these future machines in order to process this enormously important new data that's going to help with the autonomy solution. There's also going to be, I think, already we're seeing emerging needs for direct energy on board future vertical lift craft. So you don't just want a robot helicopter. You want a robot helicopter with a laser. This is like, the next shiny toy. It's an emerging need. Your distributed electric propulsion system, you're clocking battery improvements of around 8% per year in energy density. Is that right? And motors currently at 95 to 97% efficiency. How do we improve on those numbers? What has to happen?
You let time go by. And that's, you develop a critical path that isn't dependent on battery technology. Hybrid solutions are where it's at for the next 10 to 20 years, unless you're interested in short-range urban markets like Uber is, where every trip is less than 100 miles. So hybrid electric has a lot of potential, which can get you kind of the best of both worlds if you're careful about the design so you don't end up with the worst of both worlds.
Is there anything that changes in material science, new advances in energy storage materially might contribute?
Yeah, and there's $2 billion a year going into energy storage because everybody wants it for everything.
Yeah.
So it's not, I don't think it's dependent on the aerospace industry to fix that. And actually, again, from my perspective, I see 30 different battery companies doing 30 different directions in terms of exciting developments. But again, for me, it's not about batteries. For the Uber short range market, it's about pulse chargers that can recharge a battery. 20% of the battery in 45 seconds, 75% of the battery in 15 minutes. If you can do that, who cares about the batteries if you're doing these short-range trips? And if you're doing longer-term trips, then it's definitely a hybrid electric solution. But so I want to go back to one thing that you said, and that is I would love for the opportunity to compete fixed-wing VTOL with this new technology to the best helicopters, because if you're interested in speed and range, wing-borne flight is always going to be more efficient,
Right.
as long as you can avoid the horrible mechanical complexity that's been associated with fixed-wing VTOL in the past.
Right.
And that's what distributed electric propulsion does. So it's not about energy storage, because there's so many, you saw all the different concepts. There's so many different directions to go with it.
Right.
The design space has been blown open, and we're at the beginning of a 30-year renaissance in powered lift aircraft.
And would you also say that we can achieve new plateaus of onboard power as well? Because we're talking with Matt about all the different processors, all that he wants to put on there, also including data collection, but also processing that data. And that's a big requirement.
And energy storage is a long-term proposition in terms of batteries. Fuel cells, that's a whole other discussion to go to. It's going to take many years for electrical energy storage to surpass how incredible hydrocarbon fuels are.
Right, right.
And so the beauty is to come up with solutions that don't put that on their critical path in terms of the missions, markets, and opportunities that exist to use this incredible new technology.
Yeah. So, Matt, in terms of autonomy, I'm writing about different technology solutions that were used at different points in history. I'm reminded of like the first big unmanned copter that the military used effectively, and that was the K-MAX, now owned by Lockheed Martin. Between 2011 and 2013, it flew 600 unmanned missions over Afghanistan. It's actually a sort of a tremendous accomplishment in the history of human-robotic interaction. And now we're talking about its use potentially for putting out forest fires and things like that. When you talk to folks about what's needed in terms of data, in terms of processing, for better autonomous solutions in vertical lift, what are you hearing, and what are the challenges that you then confront them with?
Well, I think in the future, being able to look out a window or a windscreen and seeing a computer-generated image instead of seeing what's outside, we're there now.
Right.
For a small area, but for the ranges that these aircraft are going to have to fly, to be able to put up a computer-generated area of imagery, elevation, and then what's synthesized from sensors on board getting fed into the system, you're going to need big processors and big storage on board.
Yeah.
That's where I see the challenge. Of course, storage gets smaller every day. Terabyte hard drives are now on keychains, so we're getting smaller. That's good, but processing power is getting better. And then again, the power that it takes to run those.
Yeah. So it's going to be, you can begin to see the physical trade-offs that have kept flying cars out of our garage.
Well, the exciting thing, again, is there's consumer markets that are evolving that are pushing the autonomy.
Right.
And potentially pushing to mass markets and very high production volumes. You look at the cost of, LiDARs for, UAVs. You're getting every year almost a doubling of improvement while the cost is coming down by several factors.
Yeah. Right.
It's being able to, I think, find the applications where autonomy can be pervasive is just an incredible opportunity for DoD to achieve incredible cost efficiencies. And when you can have every single car company on the planet working on self-driving cars, there's a synergy there to take advantage.
Yeah. Yeah, no, I think so too. Is there another question in the audience? One back there, yes. We want to capture the whole thing. Yeah.
Hi, Lee Jung Greco, Flight Global. Lieutenant Colonel, my question is actually for you. I want to go back to the elevation data that you were talking about. Can you characterize right now what is the, operational loss that you have if you don't have all that data? And then secondly, you said this was more of an acquisition issue. So is this not something that you could solve by the Rapid Capabilities Office to try and push that through?
Okay, so just to clear up a couple of things, the elevation data that is provided to the service right now is what meets the requirement, and there's no capability loss with the current data that they have. Mm-hmm. They're still executing missions today with the data that we provide them. The problem that we get into is that the new data that we've collected isn't reverse compatible. So that's kind of where we are between what we've collected and are getting ready to produce and where the services are. We just can't pull the plug on what we're giving them now and say, okay, here's the new stuff.
Right.
Because now they've got to go back and redesign their systems to take it, and that costs money. Mm-hmm. And in a physically constrained environment that we're in, we don't have money just to throw at these fixes, because you got to get into is the juice worth the squeeze, right?
Right.
So for the improvement that they're going to get versus the dollars that they're going to spend to get it, probably doesn't match.
Right.
You know, and so I'm not blaming anybody. I'm not pointing any fingers, and I'm not saying this is a bad day for anybody. I'm just, where we're getting to is that we are continually updating our data sets. Our imagery is getting more precise, right? We used to produce imagery at a 10 meter level. We're down to the 1 meter, and we're going half meter. You know, we can do that, but that takes storage size. Mm-hmm. And once you exceed the storage size of a particular airframe, then you got to get a bigger storage, a bigger device, which costs money, which costs you got to palm for all that and plan for it.
So this data down to the half meter level, this is all like machine readable and coded, right? I mean, this is like structured data that could be put into some sort of autonomous flight system.
Correct.
Yeah. What's the classification on that? Is it? I mean, it's elevation data. Is it classified? I mean, some of it must be, but not all of it.
No, it's elevation data is elevation data.
So you're sitting on this data set that all of, like, Larry Page right now could use to perfect future self-flying car, self-flying helicopter algorithms, and they've never met you. They should meet you. So when we think,
popular.
Yeah, when we think of what future roles unmanned vertical lifts can play beyond putting out fires, beyond what we today think of as the dull and the dirty, what comes to first your mind, and then everyone else's, because this is something where we've really only scratched the surface.
For autonomy, mm-hmm. I mean, we're going to get there with technology, mm-hmm. and we're already there. Mm-hmm. The big piece for autonomy is going to be trust.
Yeah.
And at what point do we trust autonomy?
Right.
At what point does the government trust autonomy?
Yeah.
Amazon wants to deliver things to your house via drone.
Right. Right. And for a commander, it's a very different set of questions that you want to ask. Is there any point, Dr. Dutta, where you see in the future simulations achieving a level of credibility and persuasiveness where government decision makers will, perhaps even military decision makers on the battalion level, would trust autonomous systems to carry people? Right now, we trust them, of course, to do cargo lifts and things like this, but to carry people. What level of comfort can we have in an autonomous system as a result of a simulation?
I think I'll defer to the Colonel for a question. This is not an area of my expertise.
Yeah, it's tricky.
I'll jump in.
Yeah.
So, I mean, it's unstoppable, right? Whether autonomous vehicles takes 10, 20, 30 years, it's going to happen. We all know it. There's going to be an evolution and a progression from piloted to lesser capable piloted to fully autonomous solutions. It is one of the waves that will run over aerospace as well as other industries. Mm-hmm. And it's bigger than that. And that is, it's not just one wave of technology. Mm-hmm. It is that there's at least 4 technology frontier waves all colliding to create this incredible convergence opportunity, right? Distributed electric propulsion, autonomy, additive manufacturing, advanced sensors that are smaller and require less power, incredible computational power. All of it's coming together, and frankly, it's fundamentally going to change the capabilities in aerospace big time over the next 10 to 30 years. Embrace the wave, because there's no other choice. But realize that, it's an evolution that's going to take time to trust. And much of it is about perception, right? If you have a self-driving car from Tesla that's actively out on the road, I mean that perceived trust will happen over a 10 to 30 year period.
Yeah.
With the introduction of automobiles, right? They were called devil wagons for the first 20 years that they existed.
Yeah.
That's how much they were hated
Well,
by
they're
horse owners.
Yeah, they're still pretty bad.
So, to jump on this,
Yeah.
I think you'll see a big push of this in the commercial aviation section. I
Yeah.
mean, it gets back to the trust issue.
Yeah.
We always said that the latest and greatest commercial airline that comes off the line is going to be built. It's going to have a pilot and a dog.
Yeah.
And the dog's job is to bite the pilot in case he tries to touch something.
Yeah.
Right.
Right.
So, and the pilot's just there so the people in the back
Right.
knows that there's an air breather up front saying, okay, everything's good.
Yeah.
But trust is that point where you say, okay, I'm willing to get on this airplane and know that there's nobody in the front seat.
Yeah.
And trust takes time.
Oh, yeah.
God, think about like 10 years from now when we all get really relieved to see that dog. So we have time for one more question before we break. Or here we go, right here.
Thank you. I've noticed that we've talked a lot about technological capabilities to advance the lift portion and the capability of the aircraft. Can you talk about the impact of these technologies on maintenance and sustainment for a fleet of aircraft?
So I guess I get to go first. It's really interesting because it's, you look at the aircraft that I showed that we're doing with distributed electric propulsion. So many times I'll have people simply freak out because they'll go, you're going from 2 engines to 12 engines. Do you know what you've just done to maintenance?
Yeah.
And my answer is, do you know in those 12 engines I have less moving parts than in one of your engines? Because it's bearings, that's it. And you know how long bearings can last and how easy it is to monitor bearings to know, even predict when they're going to fail. So we need to rethink what complexity means, and certainly there's a burden of proof on us for distributed electric propulsion to prove the significantly improved maintainability and decreased maintenance cost. We haven't done that yet. We need to. But it is so obvious to me that we are going to be able to be way ahead of where many existing solutions are. And don't get me wrong, turbine engines are incredible. And they're incredible because we spent 80 years and billions of dollars perfecting them. Now we have a whole new technology that it's in its first really 10 years. Just wait till you see what happens with our 80 years of advancement, because we're already starting in so much of a better place.
Do you, just to follow on to that, is there any aspect of the plane that you're building now that couldn't be 3D printed?
So again, additive manufacturing is really cool, but it's not a catch-all. So I'll say, what are the
parts you're missing?
Yeah, the reason I'm excited about additive manufacturing is because it lets us build things that we simply couldn't build before.
Yeah.
For instance, for a small turbine engine that we want, for instance, as a range extender, a small hybrid engine. Small turbine engines are horrible because manufacturing tolerances, Reynolds numbers, everything. Turbine engines don't scale down well. They're not a scale-free technology. But when you can all of a sudden manufacture an incredibly complex internal geometry for a recuperator, which could never be manufactured before additive manufacturing without it being horribly expensive and not very effective. Now all of a sudden we have a tool to be able to make recuperators that we could only dream of even 10 years ago.
Yeah.
And when you combine recuperators with small turbines, all of a sudden small turbines start to look good.
Yeah.
So it's a really exciting time where, again, these technologies are not catch-all.
Yeah.
They need to find where they're really doing something awesome that couldn't be done before, and that's how they're going to move into the future.
All right. Well, ladies and gentlemen, we are out of time. Please join me in thanking the panel for this really fascinating discussion today.
Good guys. Awesome to meet you.
All right.
Thank you all for joining us today. Thanks to all of our distinguished panelists. Again, to Lockheed Martin for underwriting today's event. And we hope to see you again in another Defense One event or program. Thanks so much. Enjoy your day.